the water dispenser behind me, which customer had given to someone else for repair, but they couldn't fix it. Now the circuit is with me. I will try to repair it and see what the issue is that prevented it from being fixed. The circuit doesn't seem too complicated, but several parts are missing. Notably, PL1 is missing, and PU1 is also absent. I'll replace these two components and then test if the unit powers on. PL1 is an inductor, and the rest of the PCB appears to be in decent condition. I suspect that the issue might be related to the inductor or the IC on the board. Overall, the PCB seems to be in fair condition. Let's see if we can successfully repair it. Before installing the IC, we will test some key components on the PCB. First, we will examine this resistor. It appears to be a few ohms, likely around 65 ohms, although the color code is not clearly visible. I'll test it to confirm its exact resistance. This resistor is a current limiting resistor, and it's connected to the blue wire, which indicates it's linked to the neutral line. We'll test this resistor first. Next, there are several diodes on the board that must also be tested. This is crucial because if any of these diodes are shorted, or if the capacitor labeled PC1 is shorted, the IC could fail again after replacement. Before installing new components, it's important to confirm that these parts are in working condition. Additionally, I can see that someone has previously worked on this PCB. For this reason, I will thoroughly test the areas where previous repairs have been done to ensure no faulty components are overlooked. Once these checks are complete, we'll proceed with installing the remaining parts. First, let's start by checking the resistor. We'll set the multimeter to resistance mode, and as observed, it shows 8 to 9 ohms, which is correct. Next, we will move on to test PD1, and that in diode mode. The multimeter shows a voltage drop of 0.578 volts, which indicates that the diode is likely good. We'll now reverse the polarity to confirm there's no leakage or short circuit. The results show no issues, meaning this diode is functioning properly. Moving on to PD3, this diode should ideally show no value. However, the multimeter is displaying 0.002 voltage drop, indicating this diode is shorted. Reversing the polarity confirms the same result. This diode is indeed shorted. Next, we'll check PD2. In one direction, it shows 1.295 volt, which is acceptable. Reversing the polarity gives a reading of 0.471 volt, confirming this diode is also in good condition. Now, let's test the 251 ohm resistors. Since they are connected in parallel, the expected reading should be around half of their individual resistance. The multimeter shows 25 ohms, which is correct for 251 ohm resistors in parallel. Both are working fine. Lastly, we'll test the 472 resistor. The meter reads approximately 3.062 kiloohms and fluctuates slightly. Since there's a 220 microfarad, 25 volt capacitor located nearby, and likely connected in parallel with this resistor, such fluctuating behavior is normal. Now it's time to check PC1, the capacitor. We'll test it in continuity mode. If a beep occurs briefly and then stops, the capacitor is still good. However, if the beep continues without stopping, the capacitor is faulty. In this case, no beep is heard, which suggests the capacitor is in good condition. Next, we'll check the fuse, which is located inside a fuse box. Upon testing, the fuse is confirmed to be in proper working condition, so we'll close it back up. Now, we'll proceed to replace the faulty components. The replaced parts include an inductor with a value of 4.6 microhenry, a 1 ampere general-purpose diode marked as SIM, and a switching IC with the part number PN8024R, which will be installed in place of the faulty IC. Now that I've done some initial work on the circuit, let me explain the findings. I noticed a soldered point here, which is connected to the third wire leading to the microcontroller. This indicates that if the microcontroller is short-circuited, the circuit will not function. Therefore, it's important to check this. To test this, we need to check the nearby capacitor, which is grounded. Testing this capacitor will help confirm whether the microcontroller is shorted or not. I set the multimeter to continuity mode and tested the capacitor. There's no sign of a short circuit, but verifying this step is crucial to ensure the microcontroller's condition. Next, I tested another capacitor nearby. The meter gave a slight beep, which indicates that this capacitor is fine because it successfully blocked DC as intended. Following that, I checked the ULN 2001 DIC, which is a 4-pin Darlington array. Upon testing, this IC appears to be in good condition as well. I also tested the C1R4 capacitor, and it is also working properly with no issues detected. Since capacitors play a vital role, I continued testing additional capacitors on the board to ensure there were no hidden faults. The purpose of thoroughly checking all these components is to ensure that no short circuits are present. If a short circuit is overlooked, it can lead to further complications rather than solving the issue. Skipping this step can make troubleshooting even more difficult, so ensuring everything is tested properly is essential. Now we'll proceed to test the PCB, but this time using a series board. After supplying power and turning it on, there was no response. The PCB didn't power on, and no functions appeared to be active. I will try to turn it on by pressing the buttons. Let's try pressing this button. So let's turn it off. Next, instead of using the series board, I tried supplying direct power to the PCB. Ideally, if the circuit is functional, it should work both ways, in series or directly. However, even with direct power, the PCB still didn't turn on. Upon further inspection of the PCB, I discovered an issue that was preventing it from powering on. Earlier, I had tested all the PF capacitors, and they showed no signs of faults. However, I realized that I hadn't yet tested the DC capacitors. Upon checking these, I identified the faulty component, a black capacitor with a value of 4.7 microfarad, 50 volt. This capacitor was the root cause of the problem. The IC on the board has 4 pins. Pin 1 and pin 2 are ground, pin 3 is for feedback, and pin 4 is VDD, where the positive voltage supply should be present. While testing the capacitor using the continuity mode on my multimeter, I noticed that placing the probes on the capacitor's terminals produced a beep sound, which is abnormal and indicates a possible short circuit. To confirm this, I reversed the probes and found that the beep sound persisted in both directions, confirming that the capacitor was indeed shorted. I proceeded to remove the capacitor by applying heat, and after desoldering it, I rechecked the same points on the PCB. This time, there was no beep sound, confirming that the short circuit was eliminated. Lastly, I tested the removed capacitor separately, and as expected, it was completely short-circuited, producing a continuous beep on the meter. This faulty capacitor was the main issue preventing the PCB from turning on, and replacing it with a new 4.7 microfarad, 63 volt capacitor should resolve the problem. Special care was taken while installing the new capacitor, ensuring its positive and negative terminals were correctly oriented. After soldering the capacitor in place, I tested it again using the continuity mode on the multimeter. As expected, no beep sound was detected, even when reversing the probes, confirming there was no short circuit this time. Next, I tested the PCB on the series board. After installing the switch on the series board, I powered it on. The PCB successfully powered up, the relay activated, and the display turned on. Additionally, the display showed an E1 error, and the temperature setting indicated cool mode. To confirm everything further, I turned the system off and then supplied direct power to the PCB. Upon powering it on directly, the PCB successfully turned on again, and the child lock indicator appeared alongside the E1 error. The E1 error occurred because the sensor connectors, specifically the blue and red connectors, were not connected. Now, the next step is to install the PCB back into the water dispenser and test its overall functionality to ensure it's working properly. Now, we'll proceed to supply electric power to the unit. I've thoroughly checked and completed all the wiring connections. After powering it on, the unit successfully turned on and the compressor started operating. However, it's important not to let it run empty. Make sure to fill it with water before using it to ensure proper functionality. Click on the left or right thumbnail to watch our next videos and subscribe. Thank you.